Time flows relentlessly for us all, marking every moment of our existence with its unstoppable march. From the first breath we take to our final heartbeat, time governs our lives in ways both profound and mysterious. We measure it with clocks and calendars. We feel it in the lines that appear on our faces, and we experience it in the memories that fade with each passing year. But what if there were a way to break free from this eternal constraint? What if moving at the speed of light could suspend the passage of time itself, offering us a glimpse into the possibility of immortality? Tonight, we embark on a journey through the cosmos of scientific possibility, exploring one of the most fascinating questions ever posed by human curiosity. Could light-speed movement make us immortal? This question sits at the intersection of cutting-edge physics, philosophical wonder, and our deepest human desire to transcend the limitations of mortality. It challenges everything we think we know about the nature of existence, the flow of time, and the very essence of what it means to be alive. Throughout history, humans have dreamed of conquering death, of finding ways to extend life beyond its natural boundaries. Ancient alchemists searched for the elixir of life. Mythological figures sought the fountain of youth. And modern scientists pursue the secrets of aging at the cellular level. But perhaps the answer lies not in chemistry or biology, but in the fundamental laws of physics themselves. Perhaps the key to immortality is not found in a laboratory or a medicine cabinet, but in the very fabric of space and time. Light, that most fundamental force of the universe, travels at a speed so extraordinary that it defines the very structure of reality. At approximately 300 million meters per second, light sets the ultimate speed limit for everything in our universe. Nothing with mass can reach this speed, yet light itself achieves it effortlessly, racing across vast distances to bring us the glow of distant stars and the warmth of our sun. This cosmic speed limit is not just a number, it is a boundary that shapes the very nature of time and space. When we speak of light speed, we are talking about more than just velocity. We are discussing a fundamental property of the universe that governs how time flows, how space curves, and how reality itself behaves. At speeds approaching light speed, the normal rules of time begin to break down. Minutes stretch into hours, hours into days, and days into years. The faster you move, the slower time passes for you relative to the rest of the universe. This is not science fiction. It is established scientific fact, proven through countless experiments and observations. Could this manipulation of time through speed offer us the ultimate escape from mortality? Could traveling at light speed allow us to step outside the normal flow of time, watching the universe age around us while we remain forever young? These questions push the boundaries of both scientific understanding and philosophical contemplation. They force us to consider not just what might be possible, but what it would mean for humanity if such possibilities could be realized. The speed of light represents more than just a physical constant. It represents the ultimate frontier of human exploration. Just as our ancestors once looked across uncharted oceans and wondered what lay beyond the horizon, we now look toward the speed of light and wonder what lies beyond that ultimate boundary. Could crossing that threshold grant us the immortality that has eluded humanity since the dawn of consciousness? As we explore these questions together, we will journey through the fundamental laws of physics, examine the nature of time itself, and contemplate the profound implications of light-speed travel. We will discover how Einstein's theories revolutionized our understanding of time, explore the strange phenomena of time dilation, and consider whether the human body could survive such an extraordinary journey. We will delve into the quantum nature of reality and examine theoretical models that might one day make such travel possible. This is not just a story about physics and mathematics, though those concepts will guide our path. This is a story about human ambition, about our eternal quest to transcend the limitations that bind us to a finite existence. It is about the audacious dream of conquering time itself, of achieving something that was once thought impossible. Whether that dream will ever become reality remains to be seen, but the journey toward understanding it reveals profound truths about the nature of our universe and our place within it. So join us as we embark on this cosmic exploration, where the boundaries between science and wonder blur, and where the possibility of immortality awaits those brave enough to travel at the speed of light. Time is the invisible thread that weaves through every moment of our existence, yet it remains one of the most mysterious and elusive concepts in all of science. We feel its passage in the beating of our hearts, see its effects in the changing seasons, and measure its flow with the precision of atomic clocks. But what exactly is time, and how does our experience of it shape everything we understand about life, death, and the possibility of immortality? From the moment we wake each morning to the instant we drift off to sleep, time governs our lives with absolute authority. We schedule our days around its relentless march, celebrate birthdays that mark its passage, and feel the weight of years accumulating on our shoulders. Time seems to flow in only one direction, carrying us inexorably from past to future, never allowing us to return to moments we have left behind. This one-way journey through time is so fundamental to our experience that we rarely question whether it could be otherwise. The human perception of time is both remarkably consistent and surprisingly flexible. A minute spent waiting for important news can feel like an eternity, while hours spent in the company of loved ones can seem to pass in the blink of an eye. Our brains construct our sense of time from a complex interplay of biological rhythms, emotional states, and cognitive processes. The circadian clock that regulates our sleep and wake cycles, the neural networks that process memory and anticipation, and the chemical signals that influence our mood all contribute to our subjective experience of temporal flow. But time is not merely a human construct or a product of consciousness. It is woven into the very fabric of the universe itself. Every atom vibrates with temporal precision, every chemical reaction unfolds according to temporal laws, and every star burns through its fuel in accordance with the cosmic clock. The universe has been expanding for approximately 13.8 billion years, and within that vast span, countless processes have unfolded with temporal precision that defies human comprehension. Scientists have discovered that time is not the absolute, unchanging constant that our everyday experience suggests. Instead, it is a dynamic dimension that can be stretched, compressed, and manipulated under the right conditions. This revelation, first proposed by Albert Einstein in the early 1900s, fundamentally changed our understanding of reality. Time, it turns out, is not separate from space, but intimately connected to it, forming a four-dimensional continuum called space-time. The measurement of time has evolved dramatically throughout human history. Ancient civilizations tracked time through the movement of celestial bodies, watching the sun's journey across the sky and the moon's phases through the night. They built elaborate calendars and sundials, attempting to capture and quantify the passage of time with increasing accuracy. Water clocks, mechanical timepieces, and eventually atomic clocks have allowed us to measure time with ever greater precision, revealing that even our most accurate measurements are subject to relativistic effects. Light plays a crucial role in our understanding and measurement of time. The speed of light in a vacuum is exactly 299,792,458 meters per second, a value so precise that it now defines the meter itself. This speed represents the ultimate limit for the transmission of information and the propagation of causality throughout the universe. Nothing can travel faster than light, and this cosmic speed limit has profound implications for the nature of time itself. When we observe distant stars and galaxies, we are literally looking backward in time. The light from these cosmic objects has traveled for millions or billions of years to reach our eyes, carrying with it information about events that occurred in the distant past. In essence, the universe is a vast time machine, with light serving as the messenger that brings news from across the cosmic ages. This connection between light and time hints at the deep relationship that exists between motion, speed, and temporal flow. The aging process itself is intimately connected to time's passage. Our cells divide and replicate according to biological clocks. DNA accumulates damage over time, and proteins fold and unfold in temporal sequences that determine their function. The visible signs of aging, from grey hair to wrinkled skin, are all manifestations of time's effects on biological systems. If time could somehow be slowed or stopped, would these aging processes be affected as well? Different scales of time reveal different aspects of reality. At the quantum level, particles exist in superposition states that seem to defy our classical understanding of temporal sequence. Subatomic processes occur on timescales measured in fractions of seconds, so small that they challenge our ability to conceptualize them. At the other extreme, geological and cosmological processes unfold over millions or billions of years, timescales that dwarf human existence and remind us of our place in the vast temporal landscape of the universe. The psychological experience of time varies dramatically throughout our lives. Children often perceive time as moving slowly, with summers seeming to last forever and birthdays taking an eternity to arrive. As we age, time appears to accelerate, with years passing more quickly and decades blending together in memory. This change in temporal perception may be related to the way our brains process new experiences and form memories, with familiar routines creating less distinctive temporal markers than novel events. Time also plays a fundamental role in the concept of causality. Events unfold in temporal sequence, with causes preceding effects in a logical chain that extends throughout the universe. This arrow of time, pointing from past to future, is what allows us to make sense of the world around us and predict the consequences of our actions. If time could be manipulated or reversed, what would happen to the causal relationships that govern reality? The question of whether time has a beginning or an end has puzzled philosophers and scientists for millennia. Modern cosmology suggests that time itself began with the Big Bang, approximately 13.8 billion years ago. Before that moment, the concepts of before and after may have no meaning. Similarly, the ultimate fate of the universe, whether it will expand forever or eventually collapse, will determine the future of time itself. These cosmic questions about the nature of time provide the backdrop for our exploration of whether human beings might one day transcend temporal limitations. The relationship between time and consciousness raises profound questions about the nature of existence itself. Are we merely passive observers carried along by time's current? Or do we somehow participate in creating our temporal experience? Some philosophers argue that consciousness is what gives time its apparent direction, transforming the static four-dimensional block of space-time into the dynamic flow of experience. Others suggest that time exists independently of consciousness, flowing whether we are aware of it or not. Cultural perspectives on time reveal the diversity of human approaches to this fundamental concept. Western cultures tend to view time as linear and progressive, with a clear distinction between past, present, and future. Eastern philosophies often embrace cyclical concepts of time, where events repeat in endless cycles, and the present moment contains all of eternity. Indigenous cultures frequently emphasize the interconnectedness of all temporal moments, viewing time as a web rather than a line. These different cultural frameworks remind us that our understanding of time is shaped not only by physics, but by the lens through which we choose to view reality. The biological basis of timekeeping reveals how deeply time is embedded in living systems. Every cell in our body contains molecular clocks that regulate essential processes. The suprachiasmatic nucleus in our brain acts as a master timekeeper, synchronizing our internal rhythms with the 24-hour cycle of day and night. These biological clocks are so precise that they can be disrupted by jet lag, shift work, and other disruptions to our natural temporal rhythms. The fact that life itself is organized around temporal cycles suggests that any manipulation of time would have profound effects on biological systems. Memory and time are inextricably linked, with our recollections serving as markers that help us navigate the temporal landscape of our lives. Short-term memory allows us to maintain awareness of the immediate present, while long-term memory stores the experiences that define our personal history. The way we remember events shapes our perception of how much time has passed and influences our expectations about the future. Neuroscientists have discovered that the brain's temporal processing systems are distributed across multiple regions, suggesting that our sense of time emerges from the coordinated activity of complex neural networks. The concept of simultaneity becomes particularly important when considering the effects of high-speed motion on temporal experience. In our everyday lives, we assume that events that appear to happen at the same time are truly simultaneous. However, Einstein's special theory of relativity revealed that simultaneity is relative to the observer's frame of reference. Events that appear simultaneous to one observer may occur at different times for another observer moving at high speed. This relativity of simultaneity has profound implications for our understanding of causality and the nature of time itself. Temperature and time are connected in ways that extend beyond the simple observation that chemical reactions proceed faster at higher temperatures. The concept of thermodynamic time emerges from the statistical behavior of large numbers of particles, with the direction of time being determined by the increase in entropy. This connection between time and thermodynamics suggests that time's arrow may be fundamentally related to the tendency of systems to move toward equilibrium. Understanding this relationship is crucial for comprehending how high-speed motion might affect temporal flow. The quantum mechanical description of time reveals even stranger aspects of temporal reality. At the quantum level, particles can exist in superposition states that seem to transcend classical temporal boundaries. Quantum tunneling allows particles to appear on the other side of barriers without spending time crossing them, and quantum entanglement creates correlations that seem to transcend spatial and temporal separation. These quantum phenomena suggest that time at the microscopic level may be fundamentally different from our macroscopic experience. The measurement problem in quantum mechanics raises questions about the role of observation in determining temporal reality. Some interpretations suggest that the act of measurement causes the collapse of the wave function, fixing events in time. Others propose that all possible outcomes exist simultaneously in parallel timelines. These interpretations have radically different implications for the nature of time and the possibility of manipulating temporal flow through high-speed motion. Gravity's effect on time provides another crucial piece of the temporal puzzle. Einstein's general theory of relativity revealed that massive objects warp space-time, causing time to flow more slowly in regions of strong gravitational fields. This gravitational time dilation has been confirmed through precise measurements using atomic clocks at different altitudes. The fact that both motion and gravity can affect the flow of time suggests that time is not a fixed backdrop, but a dynamic aspect of reality that can be influenced by physical conditions. The philosophical implications of time's malleability challenge our most basic assumptions about reality. If time can be stretched and compressed, what does this mean for concepts like free will, moral responsibility, and personal identity? If someone could travel at light speed and experience time differently, would they remain the same person? These questions become increasingly relevant as we contemplate the possibility of using high-speed motion to escape the normal constraints of temporal existence. The search for a unified theory of quantum gravity continues to reveal new aspects of time's nature. Some theories suggest that time itself may be quantized, consisting of discrete units called chronons. Others propose that time is emergent, arising from more fundamental non-temporal processes. These cutting-edge theories may eventually provide the key to understanding how consciousness, matter, and energy interact with the temporal dimension. As we stand on the threshold of understanding how motion at light speed might affect the flow of time, we must first appreciate the profound role that time plays in shaping our reality. Time is not merely a backdrop against which events unfold. It is an active participant in the cosmic dance of existence. Understanding its nature is essential to grasping how light-speed movement might offer a path to immortality, or at least to a radically different relationship with mortality itself. The journey through time that we experience every day is both utterly familiar and deeply mysterious. We measure it with atomic precision, yet we cannot fully explain what it is. We feel its effects in every moment of our lives, yet we struggle to understand its fundamental nature. This paradox of time, simultaneously obvious and incomprehensible, sets the stage for our exploration of whether the ultimate speed of light might offer a way to transcend temporal limitations. Time flows relentlessly for us all, marking every heartbeat and every breath with its unstoppable progression. But what if there were a way to step outside that flow, to experience time in a fundamentally different way? What if the key to immortality lies not in conquering death, but in conquering time itself? As we prepare to explore the strange phenomena of time dilation, we carry with us this deeper appreciation for the mysterious dimension that governs our lives and shapes our understanding of what it means to exist in this universe. In the early 1900s, a young patent clerk named Albert Einstein revolutionized our understanding of reality with a simple yet profound insight that time is not the absolute constant we perceive it to be. Instead, time can stretch and compress, speed up and slow down, depending on how fast you are moving through space. This phenomenon, known as time dilation, represents one of the most extraordinary predictions of Einstein's special theory of relativity, and it holds the key to understanding how light-speed movement might offer a path to immortality. Imagine two identical clocks, perfectly synchronized and ticking at exactly the same rate. Now imagine that one clock remains stationary while the other is accelerated to incredible speeds, approaching the velocity of light itself. According to Einstein's equations, something remarkable happens. The moving clock begins to tick more slowly relative to the stationary one. Not because there is anything wrong with the clock, but because time itself is flowing differently for the moving timepiece. This is not science fiction or theoretical speculation. It is established scientific fact that has been confirmed through countless experiments and observations. The mathematics behind time dilation reveals the precise relationship between speed and temporal flow. As an object approaches the speed of light, time dilation becomes more pronounced. At 50% of light speed, time flows at approximately 87% of its normal rate. At 90% of light speed, time slows to about 44% of normal. At 99% of light speed, time crawls along at just 14% of its usual pace. And as an object approaches exactly the speed of light, time dilation approaches infinity, meaning that time would effectively stop for the traveler. The famous twin paradox illustrates this concept in dramatic fashion. Consider two identical twins, born at the same moment and aging at the same rate. One twin, let us call her Maria, remains on Earth throughout her life. The other twin, Sophia, becomes an astronaut and embarks on a journey to a distant star at 99% of light speed. From Maria's perspective on Earth, Sophia's journey takes many years. She watches her sister's spacecraft disappear into the cosmos and waits decades for her return. But from Sophia's perspective aboard the high-speed spacecraft, time passes much more slowly. What seems like decades to Maria feels like only months or even weeks to Sophia. When Sophia finally returns to Earth, she discovers that while Maria has aged decades, Sophia herself has aged only a fraction of that time. The twins, once identical in age, now show a dramatic difference. Maria bears the lines and grey hair of advanced age, while Sophia appears barely older than when she left. This is not due to any special technology or medical intervention, but simply because Sophia experienced time at a different rate due to her high-speed motion. She has, in effect, travelled into the future, experiencing a form of time travel that allows her to skip forward through the years. The implications of this effect become even more extraordinary when we consider what happens at the speed of light itself. At exactly light speed, time dilation becomes infinite, meaning that time would stop completely for the traveller. From the perspective of someone moving at light speed, the journey from one end of the universe to the other would take no time at all. They would experience no aging, no passage of time, no awareness of duration. In effect, they would exist in a state of temporal suspension, immune to the aging process that affects everything else in the universe. This temporal suspension at light speed suggests a possible path to immortality. If a person could somehow achieve light speed motion, they would step outside the normal flow of time. While the universe aged around them, they would remain frozen in their current state, neither aging nor changing. From their perspective, they could travel instantly to any point in the universe, arriving at their destination in the same physical state they left. Meanwhile, billions of years might pass for stationary observers, civilizations might rise and fall, and the universe itself might undergo fundamental changes. The physical basis for time dilation lies in the fundamental structure of space-time itself. Einstein discovered that space and time are not separate entities, but are woven together into a four-dimensional fabric. When an object moves through space, it also moves through time, and the faster it moves through space, the slower it moves through time. This relationship is governed by the speed of light, which serves as the universal constant that defines the geometry of space-time. The speed of light is not just a velocity, it is the fundamental rate at which cause and effect propagate through the universe. Experimental confirmation of time dilation has come from many sources. Atomic clocks flown on high-speed aircraft show the predicted time differences when compared to identical clocks left on the ground. Particles accelerated to near light speed in particle accelerators live longer than identical particles at rest, exactly as predicted by time dilation calculations. GPS satellites orbiting Earth must account for both special and general relativistic effects to maintain accurate timing. Even the light from distant galaxies shows time dilation effects, with the oscillations of distant supernovae appearing to unfold more slowly than similar events in nearby galaxies. The biological implications of time dilation are profound and largely unexplored. If time passes more slowly for a high-speed traveler, what happens to the biological processes that govern life? The chemical reactions that power cellular metabolism, the electrical impulses that carry nerve signals, and the mechanical processes that drive heartbeats and breathing would all slow down proportionally. From the traveler's perspective, these processes would continue at their normal subjective rate, but from an outside observer's viewpoint, the traveler's entire biological system would appear to slow down. This biological time dilation could indeed represent a form of extended life. If all biological processes slow down equally, then aging itself would slow down. A person traveling at high speed would not only subjectively experience less time passing, but would also undergo less biological aging during their journey. Their cells would divide less frequently, their DNA would accumulate damage more slowly, and their organs would deteriorate at a reduced rate. In essence, high-speed motion could serve as a biological preservation mechanism, slowing the aging process and extending lifespan. The psychological experience of time dilation raises fascinating questions about consciousness and subjective experience. Would a high-speed traveler be aware that time was passing more slowly? From their own perspective, time would seem to flow normally. Their thoughts would occur at the same subjective rate, their emotions would unfold with the same intensity, and their awareness would remain unchanged. It is only when compared to the outside universe that the time dilation effect becomes apparent. This suggests that consciousness itself might be intimately connected to the flow of time, with our subjective experience of temporal passage being relative to our motion through space-time. The energy requirements for achieving significant time dilation effects are staggering. To accelerate even a small object to 99% of light speed requires enormous amounts of energy. The faster you want to go, the more energy you need, and the energy requirements increase exponentially as you approach light speed. This is because mass itself appears to increase with velocity, requiring ever more energy to achieve additional acceleration. By the time you reach light speed, the energy requirements would become infinite, which is why objects with mass cannot actually reach this ultimate velocity. However, theoretical physics suggests possible ways around these energy limitations. Concepts like the Alcubierre warp drive propose methods of achieving effective faster than light travel without actually accelerating matter to light speed. Instead of moving the spacecraft, these theories suggest warping space-time itself, creating a bubble of compressed space in front of the vehicle and expanded space behind it. If such technology were possible, it might allow for the time dilation effects of high-speed travel without the impossible energy requirements. The quantum mechanical aspects of time dilation add another layer of complexity to our understanding. At the quantum level, particles naturally exist in superposition states that seem to transcend classical temporal boundaries. Some theorists suggest that quantum effects might provide alternative pathways to achieving time dilation, perhaps through the manipulation of quantum fields or the exploitation of quantum entanglement. These speculative possibilities remain largely theoretical, but they hint at potential future technologies that might make time manipulation more accessible. The relationship between time dilation and gravity provides another perspective on temporal manipulation. Einstein's general theory of relativity revealed that massive objects warp spacetime, causing time to flow more slowly in regions of strong gravitational fields. This gravitational time dilation has been precisely measured and confirmed. Interestingly, both motion and gravity produce similar effects on time, suggesting that they are manifestations of the same underlying space-time geometry. This connection between motion, gravity, and time offers multiple potential approaches to achieving temporal manipulation. As we contemplate the possibility of using time dilation for life extension or immortality, we must consider the profound implications for human society and individual identity. If some people could travel at high speeds and age more slowly than others, what would this mean for relationships, careers, and social structures? How would society adapt to citizens who could skip decades or centuries into the future? These questions become increasingly relevant as our understanding of time dilation deepens and our technological capabilities advance. The dream of conquering time through high-speed motion represents one of humanity's most audacious aspirations. It challenges our fundamental assumptions about mortality, aging, and the nature of existence itself. While the practical obstacles remain enormous, the theoretical foundation is solid. Time dilation is not speculation, but established physics, confirmed through rigorous experimentation and precise mathematical prediction. Whether humanity will ever develop the technology to harness this effect for life extension remains an open question, but the possibility tantalizingly exists within the known laws of physics. As we prepare to explore the practical limitations and challenges of light-speed travel, we carry with us this understanding of time dilation's extraordinary potential. The universe has provided us with a mechanism for manipulating time, for stepping outside the normal flow of temporal existence. Whether we can ever harness this mechanism for the benefit of human life remains one of the greatest challenges facing our species. But the theoretical pathway to temporal transcendence has been illuminated by the brilliant insights of Einstein and confirmed by the precise measurements of modern science. The dream of traveling at the speed of light captures our imagination like few other scientific possibilities. Yet the universe itself seems to have erected an insurmountable barrier that prevents any object with mass from achieving this ultimate velocity. Understanding these fundamental limitations is crucial to comprehending both the challenges we face and the creative solutions that scientists continue to explore in their quest to unlock the secrets of light-speed travel and its potential for granting immortality. At the heart of the problem lies one of the most fundamental principles in physics: the relationship between mass, energy, and velocity described by Einstein's special theory of relativity. As any object with mass accelerates through space, something extraordinary and ultimately prohibitive begins to happen. The faster the object moves, the more energy is required to accelerate it further. This is not simply a matter of overcoming friction or air resistance, but a fundamental property of space-time itself. The energy requirements do not increase linearly with velocity, but exponentially, creating an ever steeper mountain of energy demands as speeds approach that of light. Consider a spacecraft attempting to reach light speed through conventional acceleration. At low velocities, the energy required to increase speed is relatively modest and follows familiar patterns from everyday experience. Double the speed and you need roughly 4 times the energy, following the classical relationship between kinetic energy and velocity. However, as velocities approach significant fractions of light speed, this comfortable relationship breaks down entirely. At 50% of light speed, the energy requirements have already increased dramatically beyond classical predictions. At 90% of light speed, they become truly staggering. At 99% of light speed, the energy needed reaches levels that dwarf the output of entire stars. The mathematical description of this energy barrier reveals its absolute nature. According to relativistic physics, the energy required to accelerate an object to exactly light speed becomes infinite. This is not merely a practical limitation based on current technology, but a fundamental law of the universe. No amount of technological advancement can overcome an infinite energy requirement. The universe itself has decreed that objects with mass cannot reach the speed of light through conventional acceleration. This cosmic speed limit is as absolute and inviolable as any law of physics ever discovered. The reason for this infinite energy requirement lies in the relativistic relationship between mass and velocity. As an object accelerates toward light speed, its relativistic mass appears to increase from the perspective of external observers. This is not an increase in the amount of matter the object contains, but rather an increase in its resistance to further acceleration. The faster an object moves, the more massive it becomes from the standpoint of relativity, and the more energy is required to accelerate it further. At exactly light speed, this relativistic mass would become infinite, making further acceleration impossible. This mass increase effect has been precisely measured and confirmed in particle accelerators around the world. Subatomic particles accelerated to near light speeds behave exactly as Einstein's equations predict. They become increasingly difficult to accelerate as their velocities approach light speed, requiring exponentially more energy for each additional increment of velocity. No particle accelerator, no matter how powerful, has ever been able to accelerate a massive particle to exactly light speed. The cosmic speed limit holds firm at the smallest scales, just as it does at the largest. The energy scales involved in approaching light speed are truly mind-boggling. To accelerate a single kilogram of matter to 99% of light speed would require more energy than is produced by many power plants in an entire year. To reach 99.9% of light speed, the energy requirements would exceed the total energy output of entire nations. And to reach 99.99% of light speed, we would need energy resources comparable to those of multiple stars. These numbers illustrate not just the practical impossibility of light speed travel, but the fundamental barrier that the universe has erected against such achievement. Yet the human spirit of exploration and innovation refuses to accept absolute limitations, and scientists have proposed numerous theoretical approaches that might circumvent the infinite energy problem. One of the most promising concepts is the Alcubierre warp drive, proposed by physicist Miguel Alcubierre in 1994. Rather than accelerating a spacecraft to light speed, this theoretical device would manipulate space-time itself, creating a bubble of warped space around the vessel. The space in front of the craft would be compressed while the space behind it would be expanded, causing the bubble itself to move faster than light while the spacecraft inside remains stationary relative to its local space-time. The beauty of the Alcubierre drive concept lies in its potential to sidestep the mass-energy problem entirely. Since the spacecraft never actually accelerates, it never encounters the increasing mass and infinite energy requirements that prevent conventional light-speed travel. The vessel would surf along on a wave of compressed space-time, reaching its destination without ever violating the cosmic speed limit. From the perspective of external observers, the craft would appear to travel faster than light, but from the perspective of those aboard, they would never experience acceleration or the associated relativistic effects. However, even this ingenious solution faces enormous theoretical and practical challenges. The amount of exotic matter required to create an Alcubierre drive would be staggering, possibly exceeding the mass of entire solar systems. Moreover, this exotic matter would need to possess negative energy density, a property that may not exist in nature or may be impossible to produce and control with any conceivable technology. The mathematics of the Alcubierre drive work perfectly on paper, but the physical requirements push the boundaries of what might be possible, even in principle. Wormholes represent another theoretical pathway around the light-speed barrier. These hypothetical tunnels through space-time could potentially connect distant regions of the universe, allowing for near instantaneous travel between points that would normally require millions or billions of years to traverse at light speed. A wormhole would not violate the cosmic speed limit because travelers would not actually move faster than light through space. They would simply take a shortcut through higher dimensional space-time. Yet wormholes face their own seemingly insurmountable challenges. Most theoretical models suggest that naturally occurring wormholes, if they exist at all, would be microscopic and would collapse almost instantly. Creating and maintaining a wormhole large enough for human travel would likely require exotic matter with negative energy density, the same problematic substance needed for Alcubierre drives. Even if such matter could be obtained, the engineering challenges of constructing and stabilizing a traversable wormhole would be beyond anything humanity has ever attempted. Quantum mechanics offers yet another avenue for potentially circumventing classical speed limitations. Quantum entanglement creates correlations between particles that appear to operate instantaneously across arbitrary distances, seemingly violating the light speed limit for information transfer. Some theorists have speculated about quantum teleportation techniques that might allow for faster than light transportation of information or even matter. However, closer examination reveals that quantum entanglement cannot be used to transmit usable information faster than light, and quantum teleportation requires classical communication channels that are themselves limited by light speed. The concept of tachyons, hypothetical particles that always travel faster than light, has also captured scientific imagination. If tachyons exist, They might provide insights into the nature of faster-than-light phenomena and potentially offer pathways to achieving such speeds. However, tachyons remain purely theoretical, and their existence would create paradoxes related to causality and the nature of time. Most physicists doubt that tachyons exist in nature, viewing them as mathematical curiosities rather than physical realities. Another approach involves manipulating the properties of space itself. Some theories suggest that the expansion of space during cosmic inflation exceeded light speed, indicating that space-time itself is not bound by the same limitations that constrain matter and energy. If we could somehow harness the mechanisms that drove cosmic inflation, we might be able to achieve effective faster-than-light travel by riding the expansion of space itself. However, the energy scales involved in cosmic inflation are so enormous that they dwarf even the energy requirements for conventional light-speed acceleration. The search for new physics beyond Einstein's relativity continues to reveal potential loopholes in our understanding of cosmic speed limits. String theory, loop quantum gravity, and other advanced theoretical frameworks suggest that the familiar three-dimensional space we experience may be embedded in higher dimensional structures. These extra dimensions might provide pathways for faster-than-light travel that circumvent the limitations of ordinary space-time. However, these theories remain highly speculative and lack experimental confirmation. Even if we cannot achieve true light-speed travel, approaching these velocities might still offer significant benefits for life extension and time manipulation. A spacecraft traveling at 99.9% of light speed would experience profound time dilation effects, effectively allowing its occupants to skip forward through time and arrive at distant destinations with minimal aging. While not true immortality, such travel could extend human lifespans dramatically and open up exploration possibilities that span cosmic timescales. The biological challenges of high-speed travel add another layer of complexity to the engineering problems. Even if we could solve the energy and propulsion issues, the human body would face extreme stresses during acceleration to relativistic speeds. The forces involved could be lethal unless somehow mitigated, and the radiation environment encountered during high-speed travel through interstellar space could pose serious health risks. These biological limitations might require advanced medical technologies or even fundamental modifications to human physiology. Despite these formidable challenges, the pursuit of light-speed travel continues to drive scientific innovation and technological development. Research into antimatter propulsion, fusion rockets, and other advanced propulsion systems pushes the boundaries of what might be achievable within the known laws of physics. While true light speed may remain forever beyond our reach, the journey toward that goal continues to yield insights and technologies that expand human capabilities and deepen our understanding of the universe. The cosmic speed limit represents more than just a technical challenge. It embodies the fundamental relationship between matter, energy, space, and time that defines the structure of our universe. Understanding these limitations helps us appreciate both the grandeur of cosmic design and the ingenuity required to work within its constraints. Whether humanity will ever find a way to circumvent these barriers remains an open question, but the search itself continues to reveal new possibilities and push the boundaries of human knowledge and capability. The prospect of stopping time itself represents the ultimate expression of humanity's desire to transcend the mortal limitations that define our existence. If light-speed movement could somehow freeze the flow of time for a traveler, while allowing the universe to continue its cosmic dance around them, we would witness the emergence of a new form of immortality unlike anything previously imagined. This chapter explores the profound implications of temporal suspension and examines whether the manipulation of time through extreme velocity could indeed grant us escape from the relentless march toward death. At the theoretical heart of light speed, immortality, lies the concept of complete, temporal suspension. According to Einstein's equations, an object traveling at exactly the speed of light would experience infinite time dilation, meaning that time would effectively stop for the traveler. From their perspective, no time would pass during their journey, regardless of how far they traveled, or how long the journey appeared to take from the viewpoint of stationary observers. They would exist in a state of temporal stasis, frozen at the exact moment they achieved light speed, immune to aging, decay, and all the processes that normally mark the passage of time. This temporal freezing would represent a form of immortality fundamentally different from any conceived in mythology or science fiction. The traveler would not simply live forever in the conventional sense, continuing to experience life while remaining young. Instead, they would step outside the stream of time entirely, existing in a perpetual present moment that never advances to the next. Their consciousness, their physical state, their very existence would be locked in temporal amber, preserved forever at the instant they transcended the normal flow of time. But the implications of such temporal suspension raise profound questions about the nature of consciousness and experience. If time stops for the light-speed traveler, what happens to their awareness? Consciousness appears to be intimately connected to the flow of time, with thoughts unfolding in temporal sequence and memories forming through the accumulation of experienced moments. In a state of complete temporal stasis, would consciousness itself freeze, leaving the traveler in a state of suspended awareness? Or would consciousness somehow continue to operate outside the normal flow of time, creating a form of existence unlike anything we can currently comprehend? The philosophical implications of stopping time challenge our most basic assumptions about identity and continuity of self. If a person could achieve light speed and freeze their temporal existence, would they remain the same individual? Personal identity seems to depend on continuity of experience through time, with each moment building upon the previous ones to create the ongoing narrative of selfhood. In a state of temporal suspension, this narrative would cease to unfold, potentially creating a form of existence that transcends individual identity as we understand it. From the perspective of the universe around them, a light-speed traveler would become something like a temporal ghost, existing, but not participating in the ongoing flow of cosmic events. They would witness the universe age around them in what appears to be fast-forward motion, watching stars form and die, galaxies evolve and collide, and civilizations rise and fall in what seems like accelerated time. Yet from their own perspective, these cosmic changes would occur instantaneously, without the passage of subjective time to mark their progression. This asymmetry in temporal experience creates fascinating possibilities for exploration and discovery. A light-speed traveler could journey to the edge of the observable universe and return to find that billions of years had passed on Earth. Yet, they would experience the entire journey as happening in a single instant. They could witness the ultimate fate of the cosmos, observing whether the universe expands forever, collapses in a big crunch, or experiences some other cosmic destiny. In effect, they would become time travelers par excellence, able to skip forward through cosmic history without aging or changing. The concept of light-speed time travel also opens up intriguing possibilities for information gathering and preservation. A traveler could carry information about the current state of the universe forward through time, serving as a bridge between different cosmic epochs. They might witness events that would otherwise be lost to the passage of time, observing the formation of the first galaxies, the birth of the first stars, or the eventual heat death of the universe. This information could potentially be valuable to civilizations of the far future, assuming such civilizations exist and have the technology to interact with light-speed travelers. However, the practical challenges of achieving and maintaining light speed present enormous obstacles to realizing these temporal possibilities. As we explored in previous chapters, the energy requirements for accelerating any massive object to light speed are infinite, making such achievement impossible through conventional means. Even theoretical workarounds like Alcubierre drives or wormholes face their own seemingly insurmountable technical challenges. The dream of stopping time through light speed motion remains tantalizingly out of reach within our current understanding of physics. Yet even if true light speed cannot be achieved, approaching these velocities could still offer significant temporal advantages. A traveler moving at 99.99% of light speed would experience time dilation so severe that years or decades would pass in the outside universe, while only minutes or hours passed for the traveler. While not complete temporal suspension, this extreme time dilation could effectively extend human lifespan to cosmic scales, allowing individuals to witness events separated by millions or billions of years. The biological implications of extreme time dilation add another layer of complexity to our understanding of temporal immortality. If time passes extremely slowly for a high-speed traveler, all biological processes would slow down proportionally. Cellular division, protein synthesis, DNA repair, and all the other mechanisms that sustain life would operate at a fraction of their normal rate. This biological slow motion could indeed represent a form of life extension, preserving the traveler's physical state over cosmic timescales while allowing them to experience subjective time at a normal rate. The relationship between time dilation and aging becomes particularly intriguing when we consider the fundamental mechanisms that drive the aging process. Aging appears to be caused by the accumulation of cellular damage over time, the gradual breakdown of biological systems, and the exhaustion of regenerative capacity. If time itself slows down for a traveler, these aging processes would also slow down, potentially extending biological life far beyond its normal span. In effect, extreme time dilation could serve as a form of biological preservation, maintaining the traveler in a state of suspended animation while the universe ages around them. This temporal preservation could theoretically allow a single individual to witness the entire future history of the universe. They could observe the eventual merger of the Milky Way and Andromeda galaxies, scheduled to occur in approximately 4.5 billion years. They could watch as the sun exhausts its nuclear fuel and expands into a red giant, eventually becoming a white dwarf. They could even witness the ultimate fate of all stars as the universe gradually cools and enters a state of maximum entropy known as heat death. The psychological implications of such cosmic longevity are difficult to imagine. How would the human mind cope with witnessing the death of everything familiar? What would it mean to outlive not just friends and family, but entire species, planets, and star systems? The temporal isolation experienced by a light-speed traveler could be profound, beyond any loneliness ever experienced by terrestrial beings. They would become permanent outsiders to the normal flow of time, able to observe but never truly participate in the unfolding of cosmic history. Yet this temporal isolation might also offer unique opportunities for understanding and wisdom. A being who could witness the long-term patterns of cosmic evolution might develop insights into the nature of existence that would be impossible for creatures bound to normal temporal flow. They could observe the rise and fall of countless civilizations, perhaps identifying patterns and principles that govern the development of intelligence and consciousness across cosmic time. Such knowledge could be invaluable, though the question of how to share it with temporally bound beings would present its own challenges. The possibility of multiple light-speed travelers raises additional questions about the nature of temporal immortality. Would such beings be able to interact with each other while traveling at light speed? Could they form communities or societies that exist outside normal temporal flow? The physics of light-speed interaction remains largely unexplored, but the possibility suggests that temporal immortality might not necessarily mean eternal solitude. The relationship between light-speed travel and causality presents another fascinating aspect of temporal manipulation. If a traveler could move faster than light, they might theoretically be able to arrive at their destination before they left, creating the possibility of traveling backward in time. Such time travel could open up paradoxes and logical contradictions that challenge our understanding of cause and effect. However, the prohibition against faster-than-light travel for massive objects seems to prevent such causality violations, maintaining the logical consistency of the universe. The concept of temporal loops and closed time-like curves adds yet another dimension to our exploration of time travel possibilities. Some solutions to Einstein's field equations allow for the existence of closed loops in space-time, where a traveler could theoretically return to their own past. While such exotic space-time geometries would require extreme conditions and exotic matter, they suggest that the universe might permit forms of time travel that go beyond simple time dilation effects. As we contemplate the possibility of stopping time through light-speed motion, we must also consider the broader implications for human civilization and cosmic evolution. If temporal immortality were possible, it would fundamentally alter the meaning of life, death, and progress. Individuals could potentially outlive entire cosmic epochs, carrying forward the accumulated knowledge and experience of ages. Such beings might become repositories of cosmic memory, preserving the history and achievements of countless civilizations across the vast expanse of time. The dream of temporal immortality through light-speed travel represents one of humanity's most audacious aspirations, challenging the very foundations of mortality and temporal existence. While the practical obstacles remain enormous, the theoretical possibility continues to inspire scientific research and technological development. Whether we will ever achieve the ability to stop time and gain true immortality remains an open question, but the pursuit of this goal continues to expand our understanding of time, space, and the fundamental nature of reality itself. The human body evolved over millions of years to function within the gentle confines of Earth's environment, represents a marvel of biological engineering perfectly adapted to terrestrial conditions. Yet this same biological masterpiece faces unprecedented challenges when we consider the extreme conditions associated with light-speed travel. Understanding how the human body might respond to such extraordinary circumstances is crucial to determining whether light-speed immortality could ever become more than a theoretical possibility. The journey toward light speed would subject the human body to forces and conditions unlike anything experienced in the natural world. The acceleration required to reach such velocities would create gravitational forces, or G-forces, that could easily exceed the tolerance limits of human physiology. During rapid acceleration, blood would be forced away from the brain toward other parts of the body, potentially causing loss of consciousness, organ failure, and death. Even with gradual acceleration spread over extended periods, the sustained G-forces could prove problematic for maintaining normal biological function. Current human tolerance to acceleration provides a sobering perspective on these challenges. Fighter pilots and astronauts can withstand approximately 9 to 12 times Earth's gravity for brief periods before losing consciousness. Sustained exposure to even modest G-forces, such as 3 to 4 times Earth's gravity, can cause significant physiological stress. The acceleration required to reach light speed, even if spread over years or decades, would likely exceed these tolerance limits by enormous margins. The human cardiovascular system, evolved to pump blood against Earth's modest gravitational field, would struggle to maintain circulation under such extreme conditions. The skeletal and muscular systems would face equally daunting challenges during light-speed acceleration. Bones, though remarkably strong, have specific limits to the forces they can withstand. The extreme accelerations associated with light-speed travel could cause fractures, compression injuries, and long-term skeletal damage. Muscles and connective tissues would experience stress levels far beyond their evolutionary design parameters. potentially leading to tears, strains, and permanent damage. The human spine, already vulnerable to injury under normal Earth conditions, would be particularly susceptible to damage under extreme acceleration. Even if the acceleration challenges could be overcome through advanced technology or gradual velocity increases, the human body would face additional stresses once light speed velocities were achieved. The interaction between a light speed traveler and the surrounding environment could create conditions hostile to biological life. Cosmic radiation, normally filtered by Earth's atmosphere and magnetic field, would become a significant concern for travelers venturing into the harsh environment of interstellar space at relativistic velocities. At light speed, even tiny particles of interstellar dust would become devastating projectiles capable of causing catastrophic damage to biological tissue. A single grain of sand, encountered at light speed, would impact with the energy of a powerful explosive. The human body, with its delicate cellular structures and complex organ systems, would be utterly vulnerable to such high-energy collisions. Protecting biological travelers from these impacts would require shielding technologies far beyond anything currently available. The radiation environment of interstellar space presents another formidable challenge for biological light-speed travel. Cosmic rays, high-energy particles that permeate space, would become increasingly problematic as travel speeds approach light velocity. The relativistic effects of high-speed motion would cause these particles to appear even more energetic from the traveler's perspective, creating a radiation environment that could be lethal to unprotected biological organisms. DNA damage, cancer induction, and acute radiation syndrome would all pose serious threats to light-speed travelers. The biological processes that sustain human life operate according to precise temporal rhythms that could be disrupted by the extreme time dilation effects of light-speed travel. The human circadian clock, evolved to synchronize with Earth's 24-hour day-night cycle, might become confused or dysfunctional during extended periods of relativistic travel. Sleep patterns, hormone production, and cellular repair mechanisms all depend on these biological clocks, and their disruption could have cascading effects throughout the body. Cellular metabolism, the fundamental process by which our bodies convert nutrients into energy, would experience profound changes under extreme time dilation conditions. From the perspective of external observers, all metabolic processes would slow down dramatically as the traveler approaches light speed. This biological slow motion could theoretically extend lifespan by reducing the rate at which cellular damage accumulates, but it might also create unexpected complications in the delicate balance of biochemical processes that sustain life. The cardiovascular system would face unique challenges during light-speed travel. The heart, evolved to pump blood efficiently under Earth's gravitational conditions, would need to adapt to the altered physical conditions of relativistic motion. Blood circulation patterns could be disrupted by the extreme forces involved, potentially leading to cardiovascular complications. The risk of blood clots, stroke, and heart failure might increase significantly under such conditions. The nervous system, perhaps the most complex and delicate system in the human body, would be particularly vulnerable to the stresses of light-speed travel. The brain, protected by the skull but still susceptible to acceleration forces, could suffer damage from the extreme conditions. Neural function depends on precise electrical and chemical signaling, processes that might be disrupted by the electromagnetic effects associated with relativistic motion. Memory formation, consciousness, and cognitive function could all be affected by the extreme environment of light-speed travel. The respiratory system would face its own set of challenges during relativistic travel. The process of breathing, normally an unconscious and effortless activity, could become problematic under extreme acceleration conditions. The diaphragm and other respiratory muscles would need to work against increased gravitational forces, potentially making breathing difficult or impossible. Life support systems would need to compensate for these physiological limitations, providing artificial assistance for basic biological functions. The digestive system, responsible for processing nutrients and maintaining the body's energy supply, would also be affected by light-speed travel conditions. The normal functioning of the stomach, intestines, and other digestive organs depends on gravity-assisted movement of food and waste products. Under extreme acceleration or weightless conditions, digestive processes could be severely disrupted, potentially leading to malnutrition and other health complications. Bone density loss, a well-documented problem for astronauts in weightless environments, could become even more severe during extended light-speed journeys. The absence of normal gravitational loading would cause bones to lose calcium and become increasingly fragile. Combined with the potential for acceleration-related injuries, this bone loss could leave travelers vulnerable to fractures and other skeletal problems. The immune system, which protects the body from disease and infection, might be compromised by the stresses of light-speed travel. Radiation exposure, acceleration forces, and the general stress of extreme travel conditions could suppress immune function, leaving travelers vulnerable to infections and other health problems. The isolated environment of a light-speed spacecraft would make medical treatment extremely challenging, requiring advanced autonomous medical systems. Psychological and neurological effects could prove equally challenging for light-speed travelers. The extreme isolation, confinement, and stress of such a journey could lead to depression, anxiety, and other mental health problems. The altered perception of time due to relativistic effects might create psychological disorientation and cognitive difficulties. Maintaining mental health during extended light-speed journeys would require careful consideration of psychological factors and possibly pharmaceutical interventions. Despite these formidable challenges, potential solutions and adaptations could make light-speed travel more feasible for human beings. Advanced medical technologies, including nanotechnology and genetic engineering, might allow for the enhancement of human physiology to better tolerate extreme conditions. Artificial organs, enhanced skeletal structures, and improved cardiovascular systems could help overcome some of the biological limitations that currently make light-speed travel seem impossible. Suspended animation or hibernation technologies could potentially sidestep many of the biological challenges by placing travelers in a state of reduced metabolic activity during their journeys. If consciousness and biological activity could be temporarily suspended, the stresses of acceleration and radiation exposure might be more manageable. Such technologies would need to be far more advanced than current medical capabilities, but they represent a potential pathway toward making light-speed travel compatible with human biology. Gradual adaptation and conditioning might also help prepare human bodies for the extreme conditions of light-speed travel. Extended periods of training in high-G environments, radiation exposure conditioning, and other preparation techniques could potentially increase human tolerance to relativistic travel conditions. Such preparation would need to be far more extensive than current astronaut training programs, possibly requiring years or decades of conditioning. The development of advanced protective technologies, including improved radiation shielding, inertial dampening systems, and collision avoidance mechanisms, could help protect biological travelers from the harsh environment of light-speed travel. These technologies would need to be integrated seamlessly with life support systems to create a protective cocoon around human travelers. Ultimately, the question of whether humans could survive light-speed travel may depend on how willing we are to modify ourselves to meet the extreme demands of such journeys. The biological immortality promised by light-speed travel might require us to transcend the limitations of our current biological form, evolving into something more resilient and adaptable. Whether such modifications would preserve our essential humanity while granting us access to temporal immortality remains one of the most profound questions facing our species as we contemplate the possibility of conquering time itself through the ultimate velocity of light. At the smallest scales of reality, where particles dance in probability clouds and existence itself becomes a matter of quantum uncertainty, the familiar concepts of time and aging take on entirely new meanings. The quantum realm operates according to principles so fundamentally different from our everyday experience that they challenge our most basic assumptions about the nature of temporal flow and biological aging. Understanding these quantum phenomena is essential to grasping how light-speed movement might interact with the deepest levels of reality to potentially grant immortality. Quantum mechanics reveals that time at the microscopic level behaves in ways that seem almost magical compared to our macroscopic experience. Subatomic particles exist in superposition states, simultaneously occupying multiple positions and possessing multiple properties until the moment of measurement collapses their wave functions into definite states. This quantum superposition suggests that particles experience a form of temporal multiplicity, existing in several potential timelines simultaneously until interaction with the environment forces them to choose a single reality. The implications of quantum superposition for our understanding of aging are profound and largely unexplored. If the fundamental building blocks of our bodies, the atoms and molecules that comprise our cells, exist in superposition states that span multiple potential timelines, then aging itself might be understood as a quantum process. The gradual accumulation of cellular damage that characterizes biological aging could potentially be influenced by quantum effects that operate at the level of individual molecules and molecular interactions. Quantum tunneling represents another phenomenon that challenges our classical understanding of temporal progression. Particles can tunnel through energy barriers that should be insurmountable, according to classical physics, appearing on the other side without spending time crossing the barrier. This instantaneous transportation suggests that quantum particles can sometimes bypass the normal temporal constraints that govern larger-scale phenomena. If quantum tunneling effects could somehow be scaled up or harnessed at the biological level, they might offer pathways to circumventing the temporal aspects of aging. The quantum Zeno effect demonstrates how observation and measurement can literally freeze quantum evolution. When a quantum system is observed frequently enough, its evolution can be halted, trapping it in its initial state indefinitely. This quantum freezing effect bears a striking resemblance to the temporal suspension that might occur during light-speed travel. If consciousness, or some other form of observation, could interact with the quantum processes underlying biological aging, it might be possible to halt or dramatically slow the aging process through quantum mechanical means. Quantum entanglement creates correlations between particles that appear to operate instantaneously across arbitrary distances, seemingly violating the light speed limit for information transfer. While quantum entanglement cannot be used to transmit usable information faster than light, it demonstrates that quantum correlations exist outside the normal constraints of space-time. These non-local quantum connections suggest that particles can share states and properties in ways that transcend classical temporal limitations. If biological systems could harness quantum entanglement effects, they might be able to access forms of temporal manipulation that operate outside the usual relativistic constraints. The relationship between quantum mechanics and consciousness adds another layer of complexity to our understanding of time and aging. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in collapsing quantum wave functions and determining the outcomes of quantum measurements. If consciousness is indeed a quantum phenomenon, then the subjective experience of time might be intimately connected to quantum processes occurring in the brain and nervous system. This connection could potentially be exploited to manipulate temporal experience or even influence the rate of biological aging. Quantum field theory reveals that what we perceive as empty space is actually a seething sea of virtual particles and quantum fluctuations. These vacuum fluctuations represent constant creation and annihilation of particle-antiparticle pairs that pop into existence for infinitesimally brief moments before disappearing back into the quantum vacuum. The energy associated with these fluctuations, known as zero-point energy, permeates all of space and might play a role in determining the fundamental properties of matter and energy that govern aging processes. The concept of quantum coherence suggests that biological systems might maintain quantum properties at much larger scales than previously thought possible. Recent research has revealed quantum coherence effects in photosynthesis, bird navigation, and possibly even in neural microtubules within brain cells. If biological aging involves quantum coherent processes, then these processes might be susceptible to manipulation through quantum mechanical interventions that could slow or halt the aging process. Quantum decoherence, the process by which quantum systems lose their coherent properties through interaction with their environment, provides insights into how quantum effects might be preserved or destroyed in biological systems. Environmental factors such as temperature, electromagnetic fields, and molecular interactions all contribute to decoherence, causing quantum systems to behave more classically. Understanding and controlling decoherence might be key to harnessing quantum effects for life extension or temporal manipulation. The many worlds interpretation of quantum mechanics suggests that every quantum measurement creates a branching of reality into multiple parallel universes, each containing a different outcome. According to this interpretation, there exist countless parallel versions of ourselves aging at different rates or experiencing different health outcomes. Some theorists have speculated about quantum immortality, the idea that consciousness might somehow migrate between parallel universes to avoid death, always ending up in realities where survival is possible. Quantum biology, an emerging field that studies quantum effects in living systems, has revealed surprising quantum phenomena operating within biological organisms. Quantum effects have been observed in enzyme catalysis, DNA mutation processes, and neural signal transmission. These discoveries suggest that life itself might be fundamentally quantum mechanical in nature, operating according to principles that could potentially be harnessed for life extension or temporal manipulation. The quantum nature of time itself remains one of the deepest mysteries in physics. Some theories suggest that time emerges from quantum entanglement networks that connect different regions of space. Others propose that time is quantized, consisting of discrete units called chronons that represent the smallest possible intervals of temporal experience. If time is indeed quantized at the quantum level, then manipulating these fundamental time units might offer pathways to controlling temporal flow and aging processes. Quantum error correction, the mechanism by which quantum information is protected from decoherence and noise, provides insights into how biological systems might maintain their integrity over time. Living organisms appear to possess sophisticated error correction mechanisms that repair DNA damage, replace worn-out cellular components, and maintain biological function despite constant environmental challenges. Understanding these biological error correction systems from a quantum perspective might reveal new approaches to preventing or reversing aging. The quantum measurement problem, which concerns how quantum superpositions collapse into definite states, has implications for our understanding of how aging progresses from possibility to actuality. If aging involves the collapse of quantum superposition states that include both damaged and undamaged cellular configurations, then controlling this collapse process might offer ways to bias outcomes toward healthier, less aged states. Quantum computation demonstrates how quantum systems can process information in fundamentally different ways than classical systems. Biological organisms might employ quantum computational processes to optimize cellular function, repair damage, and maintain health. Enhancing these quantum computational capabilities could potentially improve the body's ability to resist aging and maintain youthful function over extended periods. The concept of quantum time crystals, structures that repeat in time rather than space, suggests that quantum systems might be able to maintain periodic motion without energy input. If biological systems could harness time crystal effects, they might be able to maintain cyclical processes like cellular regeneration without the usual energy costs and entropy increases that contribute to aging. Quantum teleportation, while limited to quantum states rather than macroscopic objects, demonstrates that quantum information can be transmitted instantaneously across arbitrary distances. If biological information could be encoded in quantum states and teleported, this might offer pathways to preserving consciousness or biological function across vast distances or time periods. The relationship between quantum mechanics and gravity, still not fully understood, might provide additional insights into how light-speed motion could affect quantum processes related to aging. Some theories suggest that gravitational effects can influence quantum decoherence and entanglement, potentially offering ways to use space-time curvature to control quantum biological processes. Quantum sensors, which exploit quantum effects to achieve unprecedented measurement precision, might eventually allow us to monitor and control aging processes at the quantum level. Such sensors could detect the earliest quantum signatures of cellular damage or aging, enabling interventions before macroscopic symptoms appear. The study of quantum effects in biological aging remains in its infancy, but early research suggests that quantum phenomena might play important roles in DNA repair, protein folding, and cellular energy production. Understanding these quantum aspects of aging could reveal new therapeutic targets and intervention strategies that operate at the most fundamental levels of biological organization. As we contemplate the possibility of light-speed travel granting immortality, we must consider how such extreme motion might interact with the quantum processes that underlie biological aging. The relativistic effects of near-light speed motion could potentially influence quantum coherence, entanglement, and superposition in ways that either enhance or diminish the quantum mechanisms that govern aging. The intersection of quantum mechanics and relativity in the context of biological systems represents one of the most fascinating and unexplored frontiers in the quest for understanding how light-speed movement might affect mortality and aging. Light serves as far more than the illumination that allows us to see the world around us. It is the fundamental messenger of the universe, the cosmic standard by which all motion is measured, and the key to understanding how space and time themselves can be manipulated. The intimate relationship between light, space-time, and gravity holds profound implications for our quest to understand whether light-speed movement could grant immortality by allowing us to step outside the normal flow of time. The speed of light represents the ultimate cosmic constant, the unchanging foundation upon which the entire structure of space-time is built. At approximately 299,792,458 meters per second in a vacuum, light speed is not merely a velocity, but a fundamental property of the universe itself. This speed defines the rate at which cause and effect can propagate through space, establishing the boundaries of causality and determining how events in one location can influence events in another. Einstein's revolutionary insight was that light speed is the same for all observers, regardless of their own motion or the motion of the light source. This seemingly simple observation led to the complete transformation of our understanding of space and time. If light speed is constant for all observers, then space and time themselves must be flexible, stretching and compressing to accommodate this fundamental invariance. This flexibility of space-time is what allows light to maintain its constant speed while simultaneously enabling the remarkable phenomenon of time dilation. The relationship between light and gravity reveals one of the most profound connections in physics. According to Einstein's general theory of relativity, massive objects warp the fabric of space-time, creating curves and depressions that we experience as gravitational fields. Light, despite having no mass, follows these curves as it travels through space, bending around massive objects like stars and black holes. This gravitational lensing effect demonstrates that light responds to the geometry of space-time itself, following the straightest possible paths through curved four-dimensional space. When light encounters extremely strong gravitational fields, such as those near black holes, remarkable effects occur that provide insights into the nature of time manipulation. As light attempts to escape from increasingly strong gravitational fields, it becomes redshifted, losing energy and stretching to longer wavelengths. From the perspective of distant observers, this redshift makes light appear to slow down as it climbs out of gravitational wells. Near the event horizon of a black hole, light becomes so severely redshifted that it appears to freeze in time, creating the illusion that time itself has stopped. This gravitational time dilation effect occurs because strong gravitational fields warp space-time in ways that slow the passage of time. Clocks run more slowly in stronger gravitational fields, and light serves as the messenger that carries this temporal information to distant observers. The relationship between gravity and time dilation suggests that manipulating gravitational fields might offer alternative pathways to achieving the time manipulation effects that we associate with light speed travel. The concept of photons, the quantum particles of light, adds another layer to our understanding of how light interacts with space-time and gravity. Photons are massless particles that always travel at light speed, existing in a state of eternal motion that never slows down or speeds up. From the perspective of a photon, time does not pass and distance does not exist. The entire journey from a distant star to our eyes occurs instantaneously from the photon's point of view, regardless of how many billions of years the journey takes from our perspective. This photon perspective offers a tantalizing glimpse into what existence might be like at light speed. If consciousness could somehow achieve the temporal state of a photon, it would experience a form of immortality through temporal suspension. The photon exists in an eternal present moment, immune to aging and decay because time simply does not flow for particles traveling at light speed. Understanding how photons maintain this timeless existence could provide insights into achieving similar states for conscious beings. The electromagnetic nature of light reveals additional connections between light speed travel and the fundamental forces that govern matter and energy. Light is composed of oscillating electric and magnetic fields that propagate through space at the cosmic speed limit. These electromagnetic waves interact with charged particles in complex ways that could affect biological systems during high-speed travel. The electromagnetic radiation produced by rapid acceleration or deceleration could potentially damage living tissue, but it might also offer opportunities for electromagnetic manipulation of biological processes. The polarization properties of light demonstrate how electromagnetic waves can be controlled and manipulated in ways that might be relevant to achieving light speed effects. Polarized light waves oscillate in specific orientations, and these orientations can be rotated and modified through interaction with various materials and fields. If the electromagnetic aspects of light speed motion could be controlled through similar polarization techniques, it might be possible to achieve some of the benefits of light speed travel without the extreme energy requirements. The wave-particle duality of light reveals the quantum mechanical nature of electromagnetic radiation and suggests that light speed phenomena might be understood from both classical and quantum perspectives. Light behaves as a wave when propagating through space, but acts as discrete particles, photons, when interacting with matter. This dual nature might offer multiple pathways to achieving light speed effects, perhaps through wave-based space-time manipulation or particle-based quantum interactions. The interaction between light and matter provides insights into how light speed motion might affect biological systems. When light interacts with atoms and molecules, it can excite electrons to higher energy states, trigger chemical reactions, and influence molecular behavior. During light speed travel, the intense electromagnetic fields associated with such motion could potentially interact with biological molecules in ways that either enhance or inhibit aging processes. Understanding these light-matter interactions could be crucial for developing safe methods of achieving light speed effects. The concept of slow light, achieved through specialized materials that dramatically reduce light speed, demonstrates that the speed of light can be manipulated under certain conditions. Scientists have successfully slowed light to speeds of only a few meters per second by passing it through specially prepared atomic gases or crystalline structures. If similar techniques could be applied in reverse, potentially speeding up other processes to approach light speed, new pathways to temporal manipulation might become available. The relationship between light speed and the structure of space-time suggests that manipulating light itself might offer ways to control time and gravity. Some theoretical proposals involve using intense laser fields to create artificial gravitational effects or to warp space-time in localized regions. If such light-based space-time manipulation were possible, it might allow for the creation of time dilation fields that could slow aging without requiring actual light speed motion. The role of light in defining the metric of space-time reveals how deeply electromagnetic radiation is woven into the fabric of reality itself. The space-time interval, which determines the proper time experienced by objects moving through four-dimensional space-time, is fundamentally defined in terms of light speed. This intimate connection between light and the measurement of time suggests that controlling light might be equivalent to controlling time itself. Gravitational waves, ripples in space-time that travel at light speed, provide another avenue for understanding how light speed phenomena affect the structure of reality. These waves, detected for the first time in 2015, demonstrate that space-time itself can oscillate and propagate disturbances at the cosmic speed limit. The study of gravitational waves might reveal new ways to manipulate space-time that could lead to controlled time dilation effects. The concept of negative index materials, which can cause light to behave in unusual ways, suggests that the normal relationship between light and space-time might be modified through advanced materials engineering. In negative index materials, light can appear to travel backward in time or exhibit other exotic behaviors that challenge our normal understanding of electromagnetic propagation. Such materials might eventually enable the creation of devices that manipulate time through controlled interaction with light. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary surface, implies a deep connection between information, light, and the structure of space-time. Since information cannot travel faster than light, the holographic principle links the speed of light to the fundamental capacity of space-time to store and process information. This connection might offer insights into how consciousness and biological information could be preserved or manipulated during light-speed travel. The study of cosmic inflation reveals that space itself expanded faster than light during the earliest moments of the universe, demonstrating that space-time is not bound by the same speed limits that constrain matter and energy. If the mechanisms that drove cosmic inflation could be understood and controlled, they might provide pathways to achieving effective faster-than-light motion by manipulating the expansion of space rather than accelerating through it. Black hole physics reveals extreme examples of how light speed, gravity, and time interact in regions of severely warped space-time. Near black holes, the combination of strong gravitational fields and extreme space-time curvature creates conditions where time dilation becomes so severe that outside observers see time nearly stop for objects approaching the event horizon. These extreme gravitational time dilation effects might provide insights into achieving similar temporal suspension through other means. The concept of wormholes, theoretical tunnels through space-time that could connect distant regions of the universe, represents another way that light speed limitations might be circumvented. While wormholes would not violate the local speed of light limit, they could potentially allow for effective faster-than-light travel by providing shortcuts through higher dimensional space-time. The physics of wormholes is intimately connected to the behavior of light and electromagnetic fields in curved space-time. As we explore the relationship between light, space-time, and gravity, we begin to see how these fundamental aspects of reality might be harnessed to achieve the temporal manipulation effects associated with light-speed travel. Whether through direct manipulation of electromagnetic fields, control of space-time curvature, or exploitation of exotic materials and phenomena, the deep connections between light and the structure of reality offer multiple potential pathways to achieving immortality through temporal suspension. The challenge lies in developing the theoretical understanding and technological capabilities necessary to transform these possibilities into practical realities that could extend human life beyond its current temporal limitations. The quest for immortality has captivated human imaginations since the dawn of consciousness, inspiring countless myths, legends, and scientific pursuits throughout history. Yet as we explore the possibility that light-speed movement might grant us escape from mortality through temporal manipulation, we must confront a fundamental question that strikes at the heart of what it means to be human. Is immortality simply a matter of stopping time and preventing aging? Or does true immortality encompass something far more profound about the nature of existence, consciousness, and identity? Traditional concepts of immortality have focused primarily on the extension of biological life, the preservation of the physical body in a state of perpetual youth and health. Ancient alchemists sought the elixir of life. Medieval scholars pursued the philosopher's stone, and modern scientists investigate cellular regeneration and genetic therapies. These approaches share a common assumption that immortality is fundamentally about preventing death by halting or reversing the biological processes that lead to aging and bodily decay. Yet this biological perspective may represent only one dimension of a far more complex phenomenon. The possibility of achieving immortality through light-speed travel challenges us to consider temporal immortality as distinct from biological immortality. If time could be stopped or dramatically slowed for a light-speed traveler, they would indeed become immune to aging in the conventional sense. Their cellular processes would slow to a crawl, their biological clock would nearly cease its ticking, and they would exist in a state of temporal suspension that preserves their physical form indefinitely. Yet this temporal preservation raises profound questions about whether such a being would truly be immortal in any meaningful sense. Consciousness represents perhaps the most crucial element in any meaningful definition of immortality. What good would it be to preserve the body indefinitely if consciousness itself were lost or fundamentally altered in the process? The relationship between consciousness and time is intimate and complex, with our sense of self emerging from the continuous flow of experiences, memories, and thoughts that unfold in temporal sequence. If light-speed travel were to disrupt this temporal flow of consciousness, the resulting immortality might be indistinguishable from a form of eternal unconsciousness. The question of personal identity becomes central to our understanding of immortality. Philosophers have long debated what makes you you across time. Is identity rooted in physical continuity, psychological continuity, or some combination of both? If a light-speed traveler experiences such extreme time dilation that billions of years pass in the outside universe, while only moments pass for them subjectively, would they remain the same person? The traveler would return to find that everyone they knew had died, their civilization had crumbled, and their entire cultural context had vanished into the deep past. This temporal displacement raises questions about whether immortality achieved through time manipulation would be psychologically sustainable. Human identity appears to be deeply connected to our relationships with others, our participation in ongoing cultural narratives, and our sense of belonging to a particular time and place. An immortal being who outlives all their contemporaries and witnesses the rise and fall of entire civilizations might experience a form of existential isolation so profound that it could be considered a kind of death in itself. Memory plays a crucial role in maintaining personal identity over time. Yet immortality achieved through light-speed travel could create severe challenges for memory and psychological continuity. If a traveler experienced subjective moments while billions of years passed in the external universe, their memories of their original time period would become increasingly distant and possibly irrelevant to their changed circumstances. The psychological burden of carrying memories across vast cosmic timescales could prove overwhelming for minds evolved to function within human lifespans. The concept of psychological immortality suggests that true immortality might require not just the preservation of consciousness, but its continued growth and development over infinite time. A consciousness that remained static and unchanging, even if preserved indefinitely, might not constitute meaningful immortality. Instead, true immortality might require the capacity for endless learning, growth, and adaptation across cosmic timescales. This raises questions about whether human consciousness, as currently constituted, possesses the flexibility and resilience necessary for genuine immortality. Social immortality represents another dimension of the immortality question that transcends mere temporal manipulation. Humans are fundamentally social beings whose sense of meaning and purpose derives largely from their relationships and contributions to their communities. An immortal being who existed in temporal isolation, watching civilizations rise and fall without being able to meaningfully participate in their development, might experience a form of social death even while biologically immortal. True immortality might require not just individual preservation, but the preservation of meaningful social connections across time. The question of purpose and meaning becomes increasingly important when considering immortality across cosmic timescales. Human lives derive much of their meaning from their finite nature, from the knowledge that time is limited and choices matter because they cannot be indefinitely repeated. If immortality removed the urgency and finitude that give life its poignancy, would existence retain its meaning? An immortal being might face the challenge of finding purpose and motivation across timeframes that dwarf human comprehension. Creative immortality offers another perspective on what true immortality might entail. Perhaps genuine immortality is not about preserving the individual indefinitely, but about creating works, ideas, and contributions that outlast the mortal form. Artists, scientists, and thinkers achieve a form of immortality through their creations, which continue to influence and inspire long after their biological death. This creative approach to immortality suggests that meaning might be found not in endless personal survival, but in meaningful contribution to the ongoing cosmic story. The relationship between immortality and wisdom raises questions about whether infinite time would lead to infinite knowledge and understanding. Would an immortal being eventually transcend human limitations and achieve godlike wisdom and perspective? Or would consciousness itself prove to have inherent limitations that prevent true omniscience? The acquisition of wisdom might require not just time, but also diversity of experience, challenge, and growth opportunities that might be difficult to maintain across cosmic timescales. Spiritual dimensions of immortality have been explored by religious and philosophical traditions throughout human history. Many of these traditions suggest that true immortality transcends physical existence entirely, involving the survival of some essential spiritual essence beyond bodily death. From this perspective, immortality achieved through light-speed travel might be missing the most important dimension of eternal existence. The preservation of the physical form and consciousness might not constitute true immortality if it fails to address the spiritual aspects of human existence. The concept of metamorphic immortality suggests that true immortality might require the capacity for fundamental transformation and evolution rather than static preservation. An immortal being might need to periodically reinvent themselves, shedding old identities and adopting new ones as circumstances change across cosmic time. This evolutionary approach to immortality would preserve continuity of existence while allowing for the flexibility and adaptation necessary to remain vital and engaged across vast timeframes. Collective immortality represents yet another dimension that transcends individual survival. Some perspectives suggest that true immortality lies not in preserving individual consciousness, but in contributing to the ongoing evolution and survival of consciousness itself, whether through biological reproduction, cultural transmission, or technological enhancement. From this view, individual immortality might be less important than ensuring the continuation and development of conscious life throughout the universe. The ethical implications of immortality raise profound questions about fairness, resource allocation, and social responsibility. If immortality through light-speed travel were possible, but available only to a select few, what obligations would immortal beings have to mortal ones? Would immortality create an unbridgeable divide between those who could escape time and those bound by normal temporal limitations? These ethical considerations suggest that true immortality might require not just individual transcendence, but the development of just and sustainable approaches to temporal transcendence. The question of whether immortality is desirable at all challenges our assumptions about the value of endless existence. Some philosophers and psychologists argue that mortality gives life its meaning and urgency, that the knowledge of eventual death motivates achievement and deepens appreciation for existence. If immortality through light-speed travel became possible, would we lose something essentially human in the process? The answer to this question might determine whether such immortality represents genuine transcendence or a form of existential impoverishment. Technological immortality suggests that light-speed travel might be only one pathway among many toward transcending mortality. Advances in artificial intelligence, consciousness uploading, nanotechnology, and genetic engineering might offer alternative routes to immortality that preserve consciousness while allowing for greater flexibility and adaptation. These technological approaches might address some of the limitations and challenges associated with biological immortality, achieved through temporal manipulation. As we contemplate the possibility of immortality through light-speed movement, we must grapple with these deeper questions about the nature of existence, consciousness, and meaning. True immortality might require not just the preservation of biological life or the manipulation of temporal flow, but a fundamental reimagining of what it means to be conscious, purposeful, and connected across cosmic timescales. The ultimate question is not simply whether we can escape death through light-speed travel, but whether the resulting existence would constitute a life worth living across the vast expanses of cosmic time. The theoretical landscape of modern physics offers a fascinating array of models and mechanisms that could potentially enable time travel and temporal manipulation, each presenting unique pathways toward achieving the immortality that has long eluded human grasp. These theoretical constructs, while often requiring exotic conditions or materials that push the boundaries of known physics, provide rigorous mathematical frameworks for understanding how the manipulation of space-time might grant us access to temporal transcendence and escape from the normal constraints of mortality. The Alcubierre warp drive stands as one of the most compelling theoretical models for achieving effective, faster-than-light travel without violating the fundamental speed limit imposed by special relativity. Conceived by Mexican physicist Miguel Alcubierre in 1994, this model proposes a mechanism for warping space-time itself, creating a bubble of compressed space in front of a spacecraft and expanded space behind it. The spacecraft would ride this wave of distorted space-time, achieving effective faster-than-light motion while remaining stationary relative to its local space. The mathematical elegance of the Alcubierre drive lies in its ability to circumvent the infinite energy problem that prevents conventional acceleration to light speed. Since the spacecraft never actually accelerates, but instead surfs on a wave of warped space-time, it avoids the relativistic mass increase that makes light speed acceleration impossible. From the perspective of external observers, the craft appears to travel faster than light, but the occupants experience no acceleration forces and remain in an inertial reference frame throughout their journey. The implications of Alcubierre drive technology for immortality are profound. If such a device could be constructed, it would allow travelers to reach distant destinations across the universe in subjectively short periods while experiencing minimal time dilation effects. This could enable exploration of cosmic phenomena and civilizations across vast distances without the extreme temporal displacement associated with conventional relativistic travel. Immortality through Alcubierre drive technology would be achieved not through temporal suspension, but through access to infinite cosmic experiences within finite subjective time. However, the practical challenges of constructing an Alcubierre drive remain staggering. The original formulation requires exotic matter with negative energy density, a substance that may not exist in nature and would be extraordinarily difficult to produce artificially. The amount of exotic matter needed would exceed the mass energy equivalent of entire solar systems, making the construction of such devices seemingly impossible with any conceivable technology. Recent refinements to the Alcubierre model have reduced these energy requirements somewhat, but they remain far beyond current technological capabilities. Traversable wormholes represent another theoretical pathway to temporal manipulation and potential immortality. These hypothetical tunnels through space-time could connect distant regions of the universe or even different time periods, allowing for near instantaneous travel across cosmic distances or movement through time itself. The mathematical foundation for wormholes emerges from solutions to Einstein's field equations that describe geometries where space folds back on itself, creating shortcuts through higher dimensional space-time. The Morris Thorne wormhole, proposed in 1988, provides a specific mathematical model for stable, traversable wormholes that could potentially be used for time travel. These wormholes would require exotic matter to prevent their collapse, but they offer the tantalizing possibility of creating time machines that could allow travel to the past or future. If one mouth of a wormhole were accelerated to near light speed while the other remained stationary, the resulting time dilation would create a temporal gradient that could be exploited for time travel. The implications of wormhole-based time travel for immortality are extraordinary. A traveler could potentially use wormhole time machines to return to earlier periods in their life, effectively resetting their aging process and achieving a form of cyclical immortality. They could also skip forward through time to avoid periods of danger or hardship, emerging in eras when advanced medical technology might offer enhanced life extension capabilities. The ability to move freely through time could provide ultimate control over mortality and aging. Yet wormholes face their own formidable challenges. Most theoretical models suggest that naturally occurring wormholes would be microscopic and would collapse almost instantaneously due to their inherent instability. Creating and maintaining a macroscopic wormhole would require the same type of exotic matter needed for Alcubierre drives, presenting similar technological obstacles. Additionally, wormhole time machines could create causality paradoxes that might be prohibited by fundamental laws of physics. Closed time-like curves represent another theoretical framework for understanding time travel and its implications for immortality. These mathematical solutions to Einstein's field equations describe paths through space-time that loop back on themselves, allowing travelers to return to their own past. The Gödel universe, rotating cosmic strings, and certain black hole geometries all permit the existence of closed time-like curves under specific conditions. The study of closed time-like curves has revealed both fascinating possibilities and troubling paradoxes. On one hand, they suggest that backward time travel might be permitted by the laws of physics under extreme conditions. On the other hand, they create logical contradictions such as the grandfather paradox, where a time traveler could potentially prevent their own birth by interfering with their past. Various resolutions to these paradoxes have been proposed, including the Novikov self-consistency principle, which suggests that the universe somehow prevents paradoxical outcomes. Quantum mechanics offers additional theoretical models for time travel and temporal manipulation that could have implications for immortality. The many worlds interpretation suggests that every quantum measurement creates branching timelines, with all possible outcomes occurring in parallel universes. Some theorists have speculated that consciousness might be able to navigate between these parallel timelines, potentially allowing for a form of quantum immortality, where consciousness always ends up in realities where survival is possible. Quantum tunneling effects provide another potential mechanism for temporal manipulation. While conventional tunneling allows particles to pass through energy barriers, some theoretical models suggest that quantum tunneling through temporal barriers might be possible under certain conditions. This could potentially allow for instantaneous or faster-than-light communication and travel, though the practical applications remain highly speculative. The concept of cosmic strings, theoretical one-dimensional defects in spacetime left over from the early universe, offers yet another model for time travel and temporal manipulation. If cosmic strings exist and move at high velocities, they could create regions of warped spacetime that permit closed time-like curves. Two cosmic strings passing by each other at relativistic speeds could theoretically create a time machine that allows travel to the past. Extra-dimensional models from string theory and other advanced theoretical frameworks suggest that our familiar three-dimensional space might be embedded in higher dimensional structures. These extra dimensions could provide pathways for faster-than-light travel and time manipulation that circumvent the limitations of ordinary space-time. If consciousness or information could somehow access these higher dimensions, new forms of temporal transcendence might become possible. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary surface, has implications for understanding how consciousness and identity might be preserved across time. If consciousness could be encoded holographically, it might be possible to store and retrieve conscious states at different points in time, potentially allowing for forms of immortality that transcend physical death. Quantum gravity theories attempt to reconcile quantum mechanics with general relativity, potentially revealing new mechanisms for space-time manipulation. Loop quantum gravity suggests that space and time themselves might be quantized at the smallest scales, consisting of discrete units that could potentially be manipulated directly. String theory proposes that fundamental particles are actually vibrating strings in higher dimensional space, opening up possibilities for controlling the basic structure of reality. Causal dynamical triangulation and other approaches to quantum gravity suggest that spacetime might have a fundamentally discrete structure at the Planck scale. If this discreteness could be exploited, it might be possible to manipulate the basic building blocks of space and time to create artificial time dilation fields or temporal manipulation devices. The study of black hole thermodynamics has revealed deep connections between gravity, quantum mechanics, and information theory that could have implications for time travel and immortality. The information paradox associated with black hole evaporation suggests that information cannot be destroyed, potentially offering pathways for preserving consciousness, even across cosmic catastrophes. Emergent gravity theories propose that gravitational effects might arise from more fundamental quantum phenomena, potentially offering new approaches to space-time manipulation. If gravity is indeed emergent, it might be possible to control gravitational effects through quantum mechanical means, opening up new possibilities for creating time dilation fields and temporal manipulation devices. The concept of time crystals, quantum systems that exhibit periodic motion in their ground state, suggests that time itself might have crystalline properties that could be exploited for temporal manipulation. While current time crystals operate on microscopic scales, future developments might enable macroscopic time crystal effects that could influence the flow of time on larger scales. Advanced propulsion concepts such as the quantum vacuum plasma thruster and the electromagnetic drive propose mechanisms for achieving high-velocity space travel without conventional reaction mass. While these technologies would not directly enable time travel, they could make relativistic travel more practical, opening up the time dilation effects of high-speed motion for potential life extension applications. The study of consciousness and its relationship to quantum mechanics continues to reveal new possibilities for understanding how awareness might interact with the fundamental structure of reality. If consciousness indeed operates through quantum mechanical processes, it might be possible to exploit these quantum effects for temporal manipulation and consciousness preservation. As we explore these theoretical models for time travel and immortality, we must remember that they represent the cutting edge of human understanding about the nature of reality. While many of these concepts remain highly speculative and face enormous practical challenges, they provide rigorous mathematical frameworks for understanding how the manipulation of space, time, and consciousness might eventually grant us access to forms of existence that transcend normal temporal limitations. The journey from theoretical possibility to practical reality may be long and difficult, but these models illuminate the pathways that might one day lead humanity toward genuine temporal transcendence and escape from the constraints of mortality. As we stand on the threshold of a new era in space exploration, with private companies launching ambitious missions and governments planning return trips to the Moon and journeys to Mars, we find ourselves contemplating possibilities that once existed only in the realm of science fiction. The convergence of advancing technology, deepening theoretical understanding, and growing human ambition suggests that the dream of light-speed travel and its potential for granting immortality may not remain forever beyond our reach. The current trajectory of space technology development reveals accelerating progress in multiple areas that could eventually contribute to achieving relativistic velocities. Propulsion systems are evolving rapidly from chemical rockets to ion drives, nuclear thermal rockets, and fusion-powered spacecraft. Each advancement brings us closer to the high specific impulse and sustained acceleration capabilities that would be necessary for reaching significant fractions of light speed. While we remain far from the exotic propulsion systems required for true light-speed travel, the technological foundation is being laid for increasingly ambitious journeys through space and time. Private space companies have demonstrated remarkable innovation in reducing launch costs and developing reusable spacecraft technologies. These economic and technological breakthroughs are making space more accessible and enabling larger-scale projects that were previously prohibitively expensive. As space infrastructure expands and costs continue to decline, increasingly ambitious missions become feasible, potentially including the construction of massive spacecraft or space-based facilities that could serve as stepping stones toward relativistic travel capabilities. The development of space-based manufacturing and resource extraction could provide the material foundation necessary for constructing the enormous structures required for light-speed travel attempts. Asteroid mining, lunar manufacturing, and orbital construction facilities could eventually provide access to vast quantities of rare materials and enable the construction of spacecraft far larger and more complex than anything possible on Earth. The scale of engineering required for light-speed travel may demand resources and construction capabilities that can only be achieved through extensive space industrialization. Nuclear fusion technology continues to advance toward practical implementation, offering the possibility of propulsion systems with far greater efficiency than current chemical rockets. Fusion rockets could potentially achieve specific impulses high enough to reach significant fractions of light speed, making relativistic travel more feasible. The development of practical fusion technology would revolutionize space travel and bring us substantially closer to the velocities required for meaningful time dilation effects. Antimatter research, while still in its early stages, holds the promise of even more exotic propulsion possibilities. Antimatter represents the ultimate energy source, with complete matter, antimatter annihilation, releasing energy according to Einstein's famous equation E equals mc squared. Even tiny amounts of antimatter could provide enormous propulsive energy, potentially enabling spacecraft to achieve velocities approaching light speed. Current antimatter production capabilities are extremely limited, but continued research could eventually make antimatter propulsion feasible for advanced spacecraft. Breakthrough propulsion physics research continues to explore theoretical concepts that could revolutionize space travel. Scientists are investigating possibilities such as manipulating inertia, creating artificial gravity fields, and exploiting quantum vacuum effects for propulsion. While these concepts remain highly speculative, they represent potential pathways to propulsion systems that could circumvent the limitations of conventional rocket technology and enable new approaches to achieving high velocities. The search for new physics beyond the standard model could reveal fundamental forces or particles that might be exploited for advanced propulsion. Dark matter and dark energy, which comprise the majority of the universe but remain poorly understood, might hold keys to new forms of energy manipulation and space-time control. As our understanding of these cosmic phenomena improves, new technological possibilities may emerge that could make light-speed travel more achievable. Artificial intelligence and machine learning are accelerating the pace of scientific discovery and technological development across all fields relevant to space exploration. AI systems are already being used to optimize spacecraft designs, plan complex missions, and analyze vast amounts of astronomical data. As AI capabilities continue to advance, they could play crucial roles in solving the enormous technical challenges associated with light-speed travel, potentially discovering solutions that would be beyond human cognitive capabilities alone. Quantum computing developments could provide the computational power necessary to model and optimize the complex systems required for light-speed travel. The quantum mechanical effects that would be encountered during relativistic travel might require quantum computational approaches to understand and control effectively. Quantum computers could potentially simulate exotic matter behavior, optimize space-time manipulation techniques, and solve the computational challenges associated with maintaining stable wormholes or Alcubierre drive systems. Nanotechnology and molecular manufacturing could enable the construction of materials and devices with properties that approach the exotic matter requirements for advanced propulsion systems. Self-assembling nanomaterials, programmable matter, and molecular-scale manufacturing could potentially create substances with negative energy density or other unusual properties required for space-time manipulation. The precision control offered by nanotechnology might be essential for creating the delicate conditions necessary for stable wormholes or other exotic space-time phenomena. Biotechnology advances could address the biological challenges of light-speed travel by enhancing human physiology to better tolerate extreme conditions. Genetic engineering, synthetic biology, and regenerative medicine could potentially create enhanced humans capable of surviving the stresses of relativistic travel. Alternatively, consciousness transfer technology might allow human minds to be housed in more durable artificial substrates that could better withstand the rigors of light-speed journeys. The development of closed-loop life support systems and sustainable space habitats is advancing rapidly, driven by plans for long-duration missions to Mars and beyond. These technologies would be essential for any attempt at light-speed travel, as such journeys could require enormous amounts of time from the perspective of external observers. Creating self-sufficient spacecraft capable of maintaining human life for centuries or millennia would be a prerequisite for practical light-speed travel. International collaboration in space exploration continues to expand, with multiple nations and organizations working together on increasingly ambitious projects. The scale and complexity of lightspeed travel development would likely require unprecedented levels of global cooperation, pooling resources and expertise from around the world. The International Space Station serves as a model for such collaboration, demonstrating that complex technical projects can be successfully pursued through international partnerships. Commercial space ventures are driving innovation and competition that accelerates technological development. The emergence of space tourism, satellite constellations, and commercial space stations is creating new markets and incentives for space technology advancement. This commercial momentum could eventually extend to more exotic technologies as companies compete to achieve breakthrough capabilities in space travel. The discovery of potentially habitable exoplanets has provided new motivation for developing interstellar travel capabilities. Thousands of exoplanets have been identified, many of which might harbor conditions suitable for life. The desire to reach these distant worlds could drive the development of propulsion technologies capable of achieving significant fractions of light speed, making interstellar missions feasible within human lifetimes. Robotic exploration missions continue to expand our understanding of the solar system and the challenges of long-duration space travel. These missions serve as testbeds for technologies that could eventually be scaled up for human interstellar travel. The lessons learned from managing complex spacecraft over decades of operation will be invaluable for designing systems capable of supporting light-speed journeys. The growing understanding of biological aging and life extension research on Earth could complement space-based approaches to achieving longevity. If conventional medical technology can significantly extend human lifespan, it would make long-duration space missions more feasible and provide more time for the development of light-speed travel capabilities. The convergence of life extension research and space technology could create synergistic effects that accelerate progress toward temporal transcendence. Educational and inspirational effects of space exploration continue to motivate new generations of scientists and engineers to pursue ambitious goals. The publicity and excitement generated by space missions inspire young people to enter technical fields and work on challenging problems. This human capital development is essential for maintaining the long-term research and development efforts that would be required to achieve light-speed travel capabilities. Economic benefits of space technology development create positive feedback loops that support continued investment in advanced research. Technologies developed for space applications often find terrestrial applications that generate economic returns, justifying continued investment in space research. This economic foundation could eventually support the massive investment required for light-speed travel development. The philosophical and cultural implications of light-speed travel continue to inspire public interest and support for space exploration. The possibility of achieving immortality through temporal manipulation captures human imagination and provides motivation for supporting ambitious space research programs. Public enthusiasm for space exploration helps maintain political support for the long-term research investments required for breakthrough technologies. As we look toward the future of space exploration and the possibility of unlocking immortality through light-speed travel, we see a convergence of advancing technologies, growing capabilities, and expanding human ambition. While the challenges remain enormous and the timeline uncertain, the trajectory of progress suggests that what seems impossible today may become achievable tomorrow. The dream of conquering time through light-speed motion may yet be realized by future generations of space explorers, opening up possibilities for human existence that transcend the temporal limitations that have defined our species throughout history. Whether humanity will ultimately achieve this cosmic transcendence remains to be seen, but the journey toward that goal continues to drive scientific discovery, technological innovation, and the expansion of human knowledge and capability across the vast frontier of space. As our exploration of light speed movement and its potential for granting immortality draws to a close, we find ourselves standing at the edge of infinite possibility, gazing into a cosmos that holds secrets we have only begun to glimpse. The journey we have taken together through the realms of physics, biology, philosophy, and human aspiration has revealed both the magnificent scope of our dreams and the profound challenges that lie ahead on the path toward temporal transcendence. Throughout our investigation, we have discovered that the question of whether light speed movement can make us immortal cannot be answered with simple certainty. The universe has provided us with tantalizing hints that such transcendence might be possible, embedded in the elegant mathematics of relativity, the strange phenomena of quantum mechanics, and the exotic possibilities suggested by cutting-edge theoretical physics. Yet these same laws of nature seem to erect formidable barriers that challenge our every attempt to breach the cosmic speed limit and step outside the normal flow of time. The infinite energy requirements for accelerating massive objects to light speed represent more than just a technical obstacle. They embody a fundamental aspect of cosmic design that appears to protect the universe from paradox and preserve the logical consistency of causality. Yet human ingenuity has already conceived theoretical workarounds that might circumvent these limitations. From Alcubierre warp drives that surf on waves of distorted space-time to traversable wormholes that provide shortcuts through higher dimensional reality, we have explored how time itself behaves at the extremes of velocity, discovering that the universe permits a form of temporal manipulation that could indeed grant escape from aging and decay. The phenomenon of time dilation, confirmed through countless experiments and observations, demonstrates that time is not the absolute constant our everyday experience suggests, but a flexible dimension that responds to motion and gravity. At light speed, this flexibility reaches its ultimate expression, potentially allowing for complete temporal suspension and a form of immortality unlike anything previously imagined. The biological challenges of light speed travel have revealed the extraordinary stresses that the human body would face during such journeys, from the crushing forces of acceleration to the devastating effects of cosmic radiation. Yet, we have also discovered potential pathways toward biological enhancement and protection that might make such travel survivable, suggesting that the marriage of human consciousness with more resilient forms might be necessary for achieving light-speed immortality. Our exploration of quantum mechanics has unveiled a microscopic realm where the familiar rules of time and causality break down, revealing phenomena that might offer alternative pathways to temporal manipulation. From quantum tunneling that allows particles to bypass temporal barriers to entanglement effects that seem to operate outside the normal constraints of space-time, the quantum world suggests that reality itself might be far more malleable than our macroscopic experience indicates. The relationship between light, gravity, and space-time has shown us that these fundamental aspects of reality are intimately connected in ways that might be exploited for temporal control. The warping of space-time by massive objects, the bending of light around gravitational fields, and the possibility of manipulating these effects through advanced technology all point toward potential methods of achieving time dilation without requiring impossible velocities. We have grappled with the deeper philosophical questions about what immortality truly means, discovering that simple biological preservation or temporal suspension might not constitute meaningful eternal existence. True immortality might require not just escape from death, but the preservation of consciousness, identity, purpose, and connection across cosmic timescales. The challenge is not merely technical, but existential, asking us to reimagine what it means to be human across infinite time. The theoretical models we have examined, from exotic matter drives to quantum consciousness transfer, represent the cutting edge of human understanding about the possible mechanisms for achieving temporal transcendence. While many of these concepts remain highly speculative, they provide rigorous mathematical frameworks for understanding how the manipulation of space, time, and consciousness might eventually grant us access to forms of existence that transcend mortality. Looking toward the future of space exploration, we see accelerating progress in multiple technologies that could eventually contribute to achieving light-speed capabilities. From fusion propulsion to quantum computing, from nanotechnology to artificial intelligence, the convergence of advancing sciences suggests that what seems impossible today might become achievable tomorrow. The timeline remains uncertain, but the trajectory of progress provides reason for cautious optimism. Yet perhaps the most important discovery of our journey is not about the specific mechanisms that might grant immortality, but about the profound questions that the pursuit of such transcendence raises about human nature and cosmic purpose. The quest for light-speed immortality forces us to confront fundamental issues about identity, meaning, consciousness, and our place in the vast universe. These questions may prove more important than the technical challenges, shaping not just how we achieve immortality, but whether such achievement would represent genuine transcendence or existential diminishment. The universe has shown us that it operates according to principles both beautiful and mysterious, revealing layer upon layer of complexity and possibility as our understanding deepens. The cosmic speed limit that seems to prohibit light-speed travel for massive objects might not represent an absolute barrier, but rather a challenge that calls forth human creativity and determination. The same physical laws that create obstacles also provide the theoretical foundations for overcoming them. As we contemplate the possibility of stepping outside the normal flow of time and achieving escape from mortality, we must remember that the journey itself has already transformed us. The pursuit of light-speed immortality has expanded our understanding of time, space, consciousness, and reality in ways that enrich human knowledge, regardless of whether the ultimate goal is achieved. The questions we have explored together will continue to drive scientific research, technological development, and philosophical inquiry for generations to come. The endless journey through time and space that we have undertaken reveals that immortality might not be found in any single breakthrough or discovery, but in the ongoing expansion of human knowledge and capability. Each advance in our understanding brings us closer to transcending our current limitations, whether through technological enhancement, biological modification, or fundamental changes in the nature of consciousness itself. Tonight, as you rest beneath the vast canopy of stars, you carry with you the knowledge that the universe holds possibilities beyond our wildest imagination. The photons of starlight that reach your eyes have traveled for years, decades, or centuries, experiencing no passage of time during their cosmic journeys. In some sense, these particles of light achieve the very immortality we seek, existing in an eternal present moment that connects us across the vast distances of space and time. The dreams and aspirations that drive our quest for immortality through light-speed movement reflect the deepest aspects of human nature, our refusal to accept limitations, and our determination to transcend the boundaries that define our existence. Whether or not we ultimately succeed in conquering time through cosmic velocity, the pursuit itself elevates us and expands the horizons of what it means to be conscious beings in an infinite universe. Rest now in the knowledge that the mysteries of time and existence continue to unfold around us, waiting to be discovered by future generations of explorers who will push further into the unknown realms of possibility. The story of light-speed immortality remains unwritten, its chapters waiting to be filled by the courage, creativity, and determination of those who dare to dream of transcending the temporal boundaries that have defined human existence since the dawn of consciousness. The cosmos calls to us across the vast expanse of space and time, inviting us to join the eternal dance of matter and energy, light and darkness, possibility an actuality that has been unfolding since the beginning of time itself. Whether we answer that call through light-speed travel, quantum consciousness transfer, or pathways yet to be discovered, the invitation remains open, and the journey toward immortality continues beneath the infinite stars.